Hello, everyone. Welcome to an optimization example that is purely rooted in business because we're going to maximize profit. So here we go. So in my example here, we are analyzing the profit when we are selling Q items. The demand curve that models the price in dollar as a function of units sold Q is given by PQ equal to minus 0.001 Q squared minus Q plus 6,000. To produce the product, the fixed cost of production is $250,000 and it costs $1,000 per unit to construct or to make. Find the number of units that maximize profit. So give the corresponding price per item that where you're going to reach that maximum profit and give also that maximum revenue. So this is a very nice question. Of course, we need to build the profit function. We know the profit function is given by revenue minus cost. And because this is a maximization problem, so an optimization problem, we first need to focus on what is the interval of optimization. And you can see here, there's no interval specified. So you need to construct your interval first before going into, hey, let's build profit, derive, and etc. So we need to focus on the interval of optimization. The good news here is that the steps are always the same. So because these are quantities that are modeling objects that are real, everything needs to be positive. So here, quantity and price needs to be positive. So here, the quantity that you're selling needs to be positive. And of course, you're going to be selling your stuff. So you want to make money. The price per item will also be positive. So because everything depends on Q, so here Q is the independent variable. So we know that any interval of optimization will start at 0 potentially. So Q cannot be negative. But what about the price? Maybe there is. So we see here the price function is a quadratic equation. There are some positive values that of Q that will make the price positive. So here we need a sign table for the price in order to find that correct interval of optimization. So here we need, we need a sign table for the price as a function of Q. So how do you do a sign table? Well, you need to find the roots of your equation. So here, because we have a quadratic equation, PQ is minus 0.01 Q squared minus Q plus 6,000. So if you use A equal to minus 0.01, B as minus 1, and C as 6,000, and you use your quadratic formula, poof, the two roots of that function are minus 3,000 and 2,000. Of course, we don't care about negative quantities, so we're going to do a sign table that will be a bit restricted to our function here. So the sign table for the price, so here we go. So cube, so poof. So we have our sign table here that I'm going to construct. So the first thing I'm going to use in order to construct the sign table is that this sign table, the first row is as a function of Q. So of course it starts at 0. And even if I have two roots, which are minus 3,000 and 2,000, I'm just going to keep the one that is positive. So 2,000 is my first root. That is very interesting. And then I'm going to check the sign before 2,000 and after 2,000. So just by doing one evaluation, actually here I can use 0. If you compute P at 0, you're going to get minus 0.010 squared minus 0 plus 6,000, which is 6,000. And that's a positive quantity. So I know the sign of the price is positive between 0 and 2,000. And then after that, if you pick any number, you can double check that, pick any number like 3,000. If you evaluate your price function at 2,000. Of course, you know, it's a quadratic equation, so that is going down. You know the next value is going to be negative. You can either do this by evaluation or by common sense, okay, basically. So anyway, so that's our sine table. So this means that our interval of optimization, so this is very, very important here. This is part of the analysis of the problem. So my interval of optimization, the quantities that we're going to consider here are going to be ranging from 0, and we're going to stop at 2000. So that's my interval of optimization. And it's part of the problem. So in this question, find the roots of your price function if it's a quadratic equation. Start at 0, and with your sine table, you will always, like here's a punchline, the interval will always be between 0 and the positive root of your quadratic equation for price, and after that's going to be negative. But anyways, I'm expecting this nice analysis in order to get the interval of optimization for your problem. And this is absolutely crucial. Okay, it's part of the optimization problem. Now that we have our interval, it is time to construct our function to optimize. So just like before, we know that the price is always going to be revenue minus cost. So that's something that we've been using a lot already. And when I do these type of problem, I find typically that starting with the cost function is easier, but it really doesn't matter. We need to model the revenue and we need to model cost. So let's start with cost here. So where the cost, so we have our fixed cost is at 25,000. And then because our cost per item is 1,000, it will be plus 1,000 times the number of units that we're producing, so times Q. So that's my cost function. What about the revenue function? Remember, revenue is always price times quantity. So here, my price is given by the formula minus 0.01 Q squared minus Q plus 6,000. And then I'm going to multiply all that by Q. So if you just distribute your Q here, you're going to get your final revenue function. So you're going to get minus 0.001 Q cubed minus Q squared plus 6,000 Q. So here we go. So profit is going to be revenue, so minus 0.001 Q cubed minus Q squared plus 6,000 Q minus cost, so minus, open a bracket here, be careful, take your time, so 250,000 plus 1,000 Q. So just be careful, make sure you put a bracket first. Since we're going to be playing with this equation, might as well simplify it. So here there's only one term with Q cubed. So my first term will be minus 0.01 Q cubed. Q cubed. There's also only one degree 2 term, so it's minus Q squared. But for the linear terms, so the terms with a Q in it, we have 6,000 minus 1,000. So that will be plus 5,000 Q minus my fixed cost, 250,000. And that's my function that we want to maximize. So if you're a Beast War fan, maximize. Anyways, so as soon as I know my profit function, I have my interval, I have my formula. Now this question is pure. How do you find the absolute maximums? Well, we need to derive, set this function equal to 0, keep only the critical points within the interval. Now we know between 0 and 2,000, and then we need to compare in order to decide where is my maximum. So here we go. So let's compute now Q sorry, P prime. So for P prime here, so here we go, P prime. So I'm just computing the derivative. It's a nice polynomial here. So the 3 falls, you're going to get minus 0.01 times 3, also known as minus 0.003 q squared. The q squared will just become minus 2q. And the 5,000 q will just become 5,000. And the constant just goes to 0. Now that we have our derivative, we need to set that derivative equal to 0. And here, what a nice coincidence. This derivative is a quadratic equation, so you can use the quad formula in order to compute the roots of that equation. And I will let you do this as an exercise that, boom, if you apply the quad formula, you will find two different roots. One that is 1,000, and 1,000 is inside my interval of optimization, but the other one is minus 5,000 over 3, which is a negative value, not within my interval of optimization. So this means that the potential maximums are either at the beginning at 0, at the end at 2,000, or in this case, right in the middle at 1,000. And in order to see which one will give you the biggest value, what we need to do is find the maximum by constructing a nice little table of values. So here we go. Again, here, remember, you get these output by evaluating your function. So here, poof. So if you evaluate your revenue function, sorry, not your revenue function, your profit function. So if you evaluate your profit function, so here in your table, my God, qu'est-ce qui se passe? Okay, so in your table here, you need to, so the way you get these numbers is you compute the profit at 0, 1,000, and 2,000, and I'll let you double check that at 0 you get minus 250,000. At 1,000 you get 2,750,000, and then at 2,000 you get minus 2,250,000. So of course the maximum value here will be achieved when Q is equal to 1,000. So poof, so the global maximum is for when Q is 1,000 unit. And because the question is also asking you to compute different things, so the first thing that you have already is the maximum profit. So here the maximum profit, poof, so we know it's just given by that value that we use to call it the biggest possible maximum. So here the maximum value, the maximum profit is 2,750,000, and the price, sorry, 2,200,000, sorry, 2,750,000. That's the maximum profit, and the price that you should set your product at is 4,000. And where did I get that 4,000? I'm not a magician. Okay, so here the only thing you have to do, we have a price function. So here you can double check, poof, that if you replace 1,000, Q equal to 1,000 in your price function that was given at the beginning, you're going to get back your $4,000, which is like the price per unit. So if you set your price, so whatever you're selling, if you sell it at $4,000, you will sell 1,000 of them, and you will make a profit of $2,750,000. All right. So for that nice example, that's it. That's all. Bye-bye.